Hello and welcome to Morehouse's Math Menagerie. Today we're going to continue our discussion on linear regression and talk about a few peripheral items and some details surrounding modeling using a line of best fit. In our previous video, we discussed this data, which was numbers of beers consumed versus blood alcohol concentration by a number of individuals. We're going to zero in on this data point in the upper right-hand corner here to discuss a few details. Here is a zoomed in look at that data point. Just a few reminders here. This black line here is our line of best fit. It models the relationship, the linear relationship between number of beers consumed and blood alcohol concentration. The red line down here represents the mean or average blood alcohol concentration by all the people in our sample. This is a single data point that someone consumed a certain number of beers, and then the Y value is their blood alcohol concentration. Looking at our model, we can say the explained deviation is the distance from our model's point to the Y hat. Remember, once we establish that there is a linear relationship, the best predicted value becomes this Y hat value up here. So we can explain why this Y hat is a better estimate than the Y bar, the mean value. So we can explain that deviation by claiming there's a linear relationship. What we can't explain is the distance from the actual blood alcohol concentration level to the expected blood alcohol concentration level. Y minus Y hat is unexplained. Our model is supposed to predict the blood alcohol concentration, but we're off by a little bit. This is our error. This is sometimes referred to as a residual, and it is an unexplained deviation. The distance from the actual to the mean is our total deviation. So we have three types of deviation happening in this problem. The type we can explain by claiming there's a linear model, the error in our model, which we cannot explain, and then the total deviation from the mean. Those are the three types of deviation, and this occurs for every single point. Now, if we take the data from all the points instead of just one, the total deviation squared here, this is going to be the actual minus the mean. This is the total squared for every single point, and then we add those all together. That's going to be our total variation for all the points. Here we have the explained variation, which is our model's prediction minus the mean. That is the explained variation. We would square that and add it all together. For the last part is the unexplained, the actual minus the predicted squared and all added up. This equation holds true for all models, that the total variation for all the points equals the explained plus the unexplained variation. Now, before you panic and start thinking you're going to have to plug a bunch of numbers in here and square things and add them up, in the regression output in StatCrunch, they give you all three of those numbers already. So here in our analysis of variance table at the bottom, this total is our total variation right here. The model row, this number right here, 5242, would be our explained variation, and the error is our unexplained variation. So when you run that least squares regression, the simple linear regression in StatCrunch, it gives you all three of those values. So don't worry about having to add up and square a whole bunch of stuff. One last thing we need to discuss here before we move into some examples in the homework is the coefficient of determination. The coefficient of determination is R squared. Now, remember, the correlation coefficient is R. So if you square R, you get R squared, which is the coefficient of determination. And the coefficient of determination represents the percent of the variability in the response variable that can be accounted for by our model. In the regression output, you'll often see it written like this, capital R dash square for R squared. Now, looking at a specific example from our number of beers consumed and blood alcohol concentration data, the output gave us an R squared of 79.98%. We would interpret that by saying 79.98% of the variability in blood alcohol content can be accounted for by our model using X equals the numbers of beers consumed. So we can explain about 80% of the variability in people's blood alcohol content using how many beers they've consumed. The other 20-ish% of the variability in blood alcohol concentration is due to other factors that are not included in our model. Now, let's jump over to the homework and work a few examples. We're going to start with number 3. The Minitab output shown below was obtained by using paired data consisting of weights in pounds of 28 cars and their highway fuel consumption amounts in miles per gallon. Along with the paired sample data, Minitab was also given a car weight of 5,000 pounds to be used for predicting the highway fuel consumption amount. Use the information provided in the display to determine the value of the linear correlation coefficient. Be careful to correctly identify the sign of the correlation coefficient. Given that there are 28 pairs of data, is there sufficient evidence to support a claim of linear correlation between the weights of cars and their highway fuel consumption amounts? All right, let's click on the Minitab output here. They give us the model, the linear model here. We have our y-intercept and our slope. And then down below, you'll see this r-square. This is the coefficient of determination. In order to find the linear correlation coefficient, we need to square root that value. Be very careful here, though, because we don't square root 63.6. We need to turn it into a decimal and say the square root of 0.636, and that gives us a value of 0.797. I want to pause here and caution you. R squared, because we're squaring a value, is always positive. However, you'll recall from previous videos that the correlation coefficient can be negative. The sign of the correlation coefficient and the sign of the slope are always the same. If we look up here at our model, we have a negative slope. So our correlation coefficient should also be negative. So I'm going to put a negative sign in front of this, in front of it, represent that negative value. If you don't put a negative value in front of that, it'll mark you wrong. You always want to check that the sign of your correlation coefficient is the same as the sign of the slope in our model. Next, it asks us, is there sufficient evidence to support a claim of linear correlation? Well, if we look at our slope here, the p-value is 0. So we would obviously reject the null that there's not a linear correlation in favor of the alternative that there is a linear relationship between these two variables. So we're going to say yes. We're going to do final check and go to the next question. All right, we're going to jump up to number 5 next. Let's read this together. Use the accompanying paired data consisting of registered boats in tens of thousands and manatee fatalities from boat encounters. Let X represent the number of registered boats and let Y represent the corresponding number of manatee deaths. Use this given number of registered boats and the given confidence level to construct a predicted interval estimate of manatee deaths. Use X equals 87 for 870,000 registered votes with a 99% confidence level. All right, let's click on our data and open it up in StatCrunch and see what we got. Once we're in StatCrunch, we're going to go ahead and run our linear regression. So we're going to regression, simple linear, number of boats in tens of thousands, and Y is manatee fatalities. Now, we already have this set up automatically to run these hypothesis tests. If you scroll down, you'll see this prediction of Y area here. It allows you to plug in an X value, and it will create a confidence interval around that value for a prediction. So it asked us to predict for 87 as the X value, and it wanted a 99% confidence interval. We can hit compute. Let's open this up a little bit. You will notice that it does the normal simple linear regression output. We have our manatees, our model manatees equal, and we have our equation here. It gives us this table. We have our R squared, our correlation coefficient, all the good stuff is here. If you scroll down to the bottom, you'll see predicted values, and it gives us these confidence intervals. Now, the actual predicted value for 87 is 74.22. Now, even though that's a point estimate, we're estimating that much, we're not 100% confident that's the actual number of manatee fatalities. So like we did before, we're going to build a confidence interval around that value. The calculator does this for you, and it's the output on the far right. So for the lower boundary for this confidence interval is going to be 43.715. 43.715. And the upper boundary is going to be 104.727. 104.727. Enter. Nice. Next question. All right, number 6 is the last one we're going to go over together, so let's dive in. Listed below are altitudes in thousands of feet and outside air temperatures in Fahrenheit recorded during a flight. Find the A, explained variation, B, unexplained variation, and C, indicated prediction interval. There is sufficient evidence to support a claim of linear correlation, so it is reasonable to use the regression equation when making predictions. For the predicted interval, use a 95% confidence level with an altitude of 6,327 feet or 6.327 in thousands of feet. All right, let's pull this up in StatCrunch. Once we're in StatCrunch, to find the explained variation, we're going to go to regression, simple linear, and run our linear regression analysis on this data. The X variable is altitude and the Y variable is temperature. Hit compute. And we can scroll down here to the bottom output, this analysis of variance table for regression model. The explained variation is this top number, this SS here, 10,770.021. So 10,000, let me just, actually, I wonder if I can just copy that. Oh man, look at that. I think we can just copy it. It has the 2 decimal places, so I'm going to click back 1 and hit enter. Nice. Unexplained variation, remember that's the error, which is this second number here, and it says to go to 5 decimal places. So we're going to copy that whole number, put it in here. Nice. And then it says find the indicated predicted interval. Well, going back to StatCrunch here, I'm just going to click edit and scroll down to this prediction of Y. It wanted us to use the X value of 6.327, and it wanted a 95% confidence level. That's correct. So we're going to hit compute again, scroll down, and our interval is given here in this bottom output. So the lower interval, it says 4 decimal places. I wonder if I can, oh man, look at me copying stuff. Copy that value for our lower boundary. Our upper boundary is this 59. Now it said 4 decimal places, 1, 2, 3, 4. All right. You got too many. Let's go 1 back, hit enter. Nice. All right. Well, hopefully today's video helped you. Please remember to use this Ask My Instructor button if you're needing help, or we can set up a Google Hangouts meeting to go over some problems together if you're struggling with the material. Thank you for joining us. Have a great day.